In this lecture, I will discuss about how the static differential relay work for a 50 MVA 132 by 33 kV transformer of vector group YND1 type. That is, the HV side is star connected and neutral is grounded, and LV side is delta connected and LV side induced voltage is lagging by that of the HV side induced voltage by 30 degree. So here the connection has been shown for the static differential relay for the 50 MVA 132 by 33 kV YND1 power transformer. So here ICT is used in the HV side CT secondary side and LV side CT secondary side. The purpose of the ICT is, so one, phase correction, number two is magnitude correction. So why phase correction is required? Phase correction is required because it is a star delta type of transformer. So whatever be the current in the HV side, in the delta side current is lagging by that of the HV side current by 30 degree, since the vector group is YAD1 type. Okay. So due to this vector group, there will be phase shift of 30 degree, and this phase shift should be eliminated in the differential current input, and that is why phase correction is required, and it is done by means of the ICT. Okay. And why magnitude correction is required? Because the CT ratio is in the HV side is not same with that of the LV side CT ratio, and in the HV side CT current is not same with that of the LV side CT HV side CT current, primary current. So the purpose of the magnitude correction is, whatever be the current in the HV side, it will convert after the ICT, it will convert the percentage of the full load current in the differential input for the HV side and LV side current. So in this video, I'll discuss how the ICT eliminate the phase mismatch and magnitude correction for the differential relay input for a 50 MVA 132 by 33 kV power transformer. So here the ICT connection has been shown for the HV side CT secondary input and LV side CT secondary input. Okay. So since the vector group is YND1 type, so ICT which is used in the HV side CT secondary is YD1 type. Okay. So in order to eliminate the phase which is phase mismatch which is occur from current is flowing from the HV side to LV side, YD1 type vector group of ICT is used. Okay. And the CT ratio is chosen based on the CT ratio and the full load current. So here the full load current in the HV side is 218.7 ampere, and for LV side the full load current is 875 ampere. So here the CT ratio is 300 by 1. So if the full load current will flow in the CT secondary side, 0.729 ampere current will flow for each phases, and in the delta side each phase current will be 0.577 ampere. So in the line side the current will be 0.577 into root 3 times, which is 1 ampere. So the purpose is, whatever be the current, full load current in the HV side, it will make, by means of the ICT, it will make 1 per unit current in the differential relay input. So this is how the ICT ratio is chosen. That is why the ICT ratio is 0.729 is to 0.577. So another reason for choosing star delta type of transformer in the HV side CT secondary side, since it is a star connected and star point is neutral, due to flow of the earth current, earth fault, zero sequence current will flow, and this zero sequence current will be trapped in the delta side of the transformer and it will not flow in the line side. So there will be a mismatch of the zero sequence current. So in order to eliminate this zero sequence current, star delta type transformer is chosen. So it will trapped in the delta side of the ICT secondary side. It will not flow towards the differential input. Okay, and that is why star delta type transformer is chosen. So in the LV side, since the LV side the CT ratio is 1000 by 1 and LV side full load current is 875 ampere. So due to flow of the 875 ampere, the current which is flow in the CT secondary side is 0.7875 ampere, and that is why the ICT ratio is chosen as 0.875 is to 1. Okay, and here the ICT vector group is YY0. Okay, so there is no phase shift between ICT primary and ICT secondary side current. So if 8.875 ampere current will flow in the ICT primary side, 1 ampere current will flow in the differential input current. Okay, so in the LV side, whatever be the full load current, it will make 1 per unit current in the ICT secondary side or differential input current. Now let us discuss how the ICT convert the full load current to 1 per unit current in the differential input current. So since the full load current flows in the HV side, there is a full load current is 218.7 ampere for red, yellow and blue phase, and it is 120 degree apart for yellow and blue phase respectively. There is for red phase it is 218.7 at an angle 0 degree, 218.7 at an angle minus 120 degree for yellow phase, and for blue phase it is 218.7 at an angle 120 degree. So in the if the current flows in the CT primary side from P1 to P2 direction, there will be current will flow from the S2 to S1 direction in the LV side. So there will be no phase shift if the current flows from the P1 to P2 direction, and in the secondary side if current flows from the S2 to S1 direction. Okay. So since the CT ratio is 300 by 1, the ICT primary current will be 0.729 at an angle 0 degree for red phase, 0.729 at an angle minus 120 degree for yellow phase, and 0.729 at an angle plus 120 degree for blue phase respectively. And since the ICT ratio is 0.729 is to 0.577, in the delta side, the phase current will be 0.777 at an angle 0 degree. For yellow phase, it is 0.577 at an angle minus 120 degree, and for blue phase, it is 0.577 at an angle plus 120 degree. Since the line current is this line current will be red phase current minus blue phase current. Okay, and for Y phase, this line current will be yellow phase current minus red phase current. Okay, and blue phase current will be this blue phase current minus this yellow phase current. Okay, so IR is the input current for the differential relay, which is equal to 1 at an angle minus 30 degree. That is equal to 0.5777 at an angle 0 degree minus 0.577 at an angle 120 degree, which comes as 1 at an angle minus 20 degree. Again, for the yellow phase line current or differential input current is 0.577 at an angle minus 120 degree minus 0.577 at an angle 120 degree, which comes as 1 at an angle minus 150 degree. And for blue phase, it is 0.577 at an angle minus 120 degree minus 0.577 at an angle minus 120 degree, which comes as 1 at an angle minus 90 degree. Okay. So in the LV side, the full load current is 875 ampere. Since it is a star delta type of transformer and vector group is YN D1 type, so there will be a phase shift of minus 30 degree when current flows from the HV side to LV side. Okay. So in the yellow phase, it will be 875 at an angle minus 150 degree, and for blue phase, it is 875 at an angle 90 degree. And since the current is flowing from P2 to P1 direction in the CT primary side, there will be current flows from S1 to S2 direction. Okay. On due to flow of this current from P2 to P1 direction, there will be a phase shift of 180 degree in the CT secondary side. So ICT input current or CT secondary current will be 0.875 at an angle minus 150 degree, since there is a phase shift of 180 degree that of the between HV side CT and LV side CT. Okay, So here at an angle 875 at an angle minus 30 degree current is flow in the CT primary side, and since the CT ratio is 1000 by 1, the magnitude will be 0.875 ampere and the phase angle will be minus 30 plus 180, which is equal to 0.875 at an angle 150 degree. Similarly, for yellow phase, it will be 0.875 at an angle plus 30 degree. Minus 150 plus 180 is equal to plus 30. Okay. And for blue phase, it will be 0.875 at an angle minus 90 degree. Plus 90 plus 180 is equal to 270 degree, that is minus 90 degree. Since the ICT ratio is 0.875 is to 1, okay. So 1 is the ICT secondary input and 0.87 is the primary input ratio, okay. So if the 0.875 ampere current flows in the ICT primary side, 1 ampere current will flow in the ICT secondary side or relay input current. So here the current will be 1 at an angle 150 degree for red phase. For blue phase, white phase, it will be 1 at an angle 30 degree, and for blue phase, it will be 1 at an angle minus 90 degree. So this is the restraining coil of the differential relay, and this is the operating coil of the differential current. So here the differential current will be the vector sum of these two current. Okay. So here the vector sum of two current is 1 at an angle minus 30 degree plus 1 at an angle 150 degree, which comes as 0. Again, for yellow phase, the vector sum of this current plus this current is 1 at an angle 150 degree plus 1 at an angle plus 30 degree, which is again 0. And for blue phase, the operating current will be 1 at an angle 90 degree plus 1 at an angle minus 90 degree, which is again 0. So during the normal operation, first the ICT convert whatever be the primary current, it will convert the differential input current as the percentage of the full load current for both the HV side and LV side. Again, uh, the operating coil current will be the vector sum of the two input current, and the restraining current will be the sum of the scalar sum of these two current or average of these two current. Okay. So this is how the ICT is used in case of static differential relay, and this is how the actual differential current and restraining current is calculated in case of static differential current.